Benjamin's awesome background, and meanwhile, I have a light and a plant.
I
Nothing
like your light and
particularly
plant.
spacey.
Well, yours demonstrates the ability to keep something alive, whereas no. Behind me, I have the shredded up relatives of your living plants.
At least you're making good use of them. Oh man,
Yeah.
I'm I'm very excited for this episode. Like more than usual, I think. Because I feel like,
Really? Nice.
well, I feel like,
Yeah, I was excited when it was
well,
just you and me talking. I was really excited about
I feel
that.
like
But
I feel like that's just putting more pressure on me, nothing else.
oh, you better perform, buddy.
it's not so much about, yeah. Don't feel pressure to perform. This is just a conversation. But yes, Benjamin. As much as I love our chats together, and I love all of our guests equally. Um,
Yes.
our guests, especially recently, there've been a lot of people who come from kind of different academic backgrounds to me. And so it's really cool to have someone who is also coming from the world of astronomy and working on stuff that is kind of like, I it's different enough that it's like, wow, this is new, this is cool, but not so different that I don't understand it at all.
I get what you mean.
All right, so for those who are just listening and cannot see our faces and the face of our guest, this week on Science Actually Presents The Nerd and the Scientist, we are joined by PhD candidate Naman Bajaj. And Naman, thank you so much for joining us. How's it going?
Again, thanks for having me. I mean, it's going great. I just had a few meetings again discussing science, so this sounds like a perfect day, perfect time to do a nerd and the scientist.
Yeah. You had some meetings about science talks. It's a good time for science talks. Love it. A little consistency for your day. It's nice.
Maybe I can share some secret results. And yeah,
Ooh, okay. We could have a first, first reported by the nerd and the scientist. Take
That would
that,
be actually really cool.
nature embargoes.
I still don't get that. I love it, and I think it's cool, and it adds to the whole, James Bond mystery of scientists that I've been observing. That you guys
You
have
mean James Webb
secrets,
mystery?
but then it's just like, I get it, but it's sad. I don't. They gotta keep secrets.
Well, I mean, for some of the discoveries, like some that we're going to be discussing today, I think that it's certainly worth kind of dropping that paper with a bang, rather than just you publish it, goes to the journal, and that's it. Here, we have these discoveries that they're impactful, and if we don't draw a little bit of attention to them and do a little bit of a press release, like I saw you had a cool press story with space.com, like that's the stuff that shares it outside of the bubble of the research group, and it gets other scientists interested and aware, and it gets the people interested and aware. So I think it's doing that within the framework of an embargo, I think it increases the impact.
I personally feel there are two types of secrecy really. One is among the scientists and one is between the scientists and the public. And I think the difference is among the scientists, you sort of need to have that because, or the reason we have that is because sometimes there are some bad characters or bad players in the field who may be quicker than you to publish something that was your idea or was your result, but they published it first. So your year long effort just goes to waste. And this can particularly happen with like PhD students and so on. And I think the other kind of secrecy between which is more of scientist public, I think it's more of I think taking care of that you're not sending wrong results to the people. So you're being very careful that all the review has been done, all the analysis has been done, and only then going out to the people and you're like, okay, we have this result. Even then, I think we fail sometimes, but I think that's the idea.
Two fair points. Because in the movies, if they find aliens, they keep that secret, but really not for too long at all. And I think that's got to be the most secret stuff. So just seeing a planetary disk forming It's like it's not like it's a planetary disk coming to
Fair
get
enough.
us. You know.
Fair enough.
I mean, since we're talking about planetary disks, can we please talk about this incredible James Webb data that you have? I was just looking over some of the figures before. So this paper that was published last year, I believe, um, class 1 and 2 jets with JWST, mass loss rates, asymmetries, and binary induced wiggles, which we'll get to the wiggling, but this data is exquisite. If you look at the paper, you see this image, which I think is one of the most like, it's pretty, but it's also incredibly informative, because you can basically see with these four different proto star systems that Naman, I'll let you in a moment explain what that is. You can basically see these jets being launched off the systems, and how they look at different wavelengths. So what what tell us
Yeah, let's start with that. What?
So essentially, the idea is, right. I mean, one of the questions that we have is how planets form. Like, how do you make these planets? And it would have been a relatively straightforward question to answer if you just looked at the solar system. You have four rocky planets, two gas giants, two ice giants, all arranged sequentially, which sort of makes sense because the rocky planets receive more energy from the sun, so they lose their atmosphere. The gas giants have it. The ice giants, they're in the cold, far out region, so they're cold and they're icy. All makes sense. Things sort of changed, I think, when we looked at planets around other stars, and we found all sorts of weird things. Like the first planet we found was a Jupiter-like planet, but so close to the host star that Mercury is 10 times away from Sun. It's like
Yep.
really just around the star. And then you sort of have to ask this question, okay, how are these forming? And then we found today we have, I think, about 6,000 exoplanets, and then they come in all sort of shapes and sizes and varieties and flavors. So how do you make them? So there are, I think, two ways to answer that. One is you look at objects in the solar system, which is what a lot of people in my department do, because Earth has been altered, life on Earth has been altered. But if you look at asteroids, they have been the same, pretty much the same, for 4.5 billion years. So you can just you know research them, and exactly what was happening sort of 4.5 billion years ago. The other way, which is what we do, is we actually look at planets forming right now, and that is where James Webb comes in, because it's super powerful telescope. So what we do, we have a database of at this point I think more than 1,000 stars, which are very young. To put in context, our solar system is 4.5 billion years old. These stars are a few million years old, so these are more than 1,000 times younger than our sun, and
Babies.
they have
Yes.
not made planets, right? So they have a young star at the center, which is still forming. It has not started nuclear reactions inside and so on, and it has a large disk of dust and gas. This is the raw material for planets, right? So this is where your planets are going to form. They haven't formed yet, but everything that happens in this disk is going to dictate what planets, what sizes, where in the disk, and so on. So that's why we want to study these disks, to see what the outcome is and sort of match the outcome, and then you can trace it back and say how solar system formed, which I think a very interesting question to answer. So when we're doing this, one of the phenomena that we found, and it seems very common, is that you have this. So think of looking at the solar system from the side view, right? So you have the star here, you have the planets all in this line. Now these disks, at the younger stage, they are ejecting material perpendicular to the disk. And how far are we from the sun? About an AU. That's the definition of AU,
Hmm.
right? The size of the solar system, 50 AU. These jets, this gas is going out to thousands of AU
Well,
from the star and from this disk. And then you kind of answer the question, it, I mean, has to come that if they're so obvious, they're everywhere and they're huge, they're massive, then what is their role in forming these planets? They have to play some role. They're not just there, or uh, they're not just happening without a reason, right? There is some physics behind it, and that some physics is linked to how planets form. So that is sort of what we are trying to understand. And James Webb, because it gives images, but also images at different wavelengths. So you can go to a particular tracer, Like for example, I can see how much what is iron tracing. Where is iron in my disk?
Hmm.
And it turns out all the iron is in the jet. That the ionized iron, of course. You can see sulfur, you can see carbon. So that is sort of what we showed in that paper. That a bunch of these lines, they're all tracing jets, and then you can, of course, now this is just the fact that jets exist, but then they are also weird in a sense that one disk, which is supposed to be symmetric on the two sides, is ejecting a longer jet on one side and a shorter jet on the other side. A faster jet on one side, a slower jet on the other side, which again has to be linked back to the physics in the disk, which
Right.
is forming planets. So that is sort of the broader overview of what we are trying to do.
Across all the stars that you studied for this research,
Uh-huh.
is that kind of like a pattern that you've seen? It's stronger on one end and slower on the other. There's never any that's kind of equal on up and down,
No,
or does
there are
it say?
equals as well. So we studied
Oh,
in that particular paper that we published last year, there were four objects. So
Hmm.
two of them seem to be symmetric, two of them seem to be normal, and two of them seem to be asymmetric. And even in the past, people have shown, or at least there was one study that sort of suggested that this asymmetry is in 50% of the disks. So it has to do with the magnetic fields, so alignment of the magnetic field of the disk and the star. So apparently, in 50% of the cases, it will be aligned. In 50% of the cases, it will not be aligned. And but we don't know. We don't know. That's what doing. I mean, that's one of the ideas.
It's so
that's
weird
crazy.
for me to think of jets coming from a protostar, a baby star, because a lot of the work that I do is more like transients, right? And you're talking
Mhm.
about jets there that are being launched from black holes or supermassive black holes. So, do we understand anything about the physics of how these jets are being launched from the protostars?
Um, so I think we are at a point where we've stopped saying that the jets are being launched from the star. I
Hmm.
think we are starting to agree that they are launched from the disk and not the star.
Okay.
So it has to do with the magnetic field of the disk. It can be, the magnetic field itself. There could be something from the star, the stellar magnetosphere, that could be interacting and then ejecting them. But the current idea that we have is that the disk itself has a vertical magnetic field.
Hmm.
So any material, any particle that will get coupled or sort of, it will agree to do what the magnetic field says. It will just follow the magnetic field lines and then, leave the system
Hmm.
perpendicular. And we don't have just jets, but we also have winds. So, and whenever I say winds, or whenever I start thinking of a press release which says winds, I have to always remind myself winds are not these. What most people think of winds is not this. So winds is just, it is like jet, but it is moving slower. So these jets are very fast. These are 100 kilometers per second speed gas, right? Winds are slower in astronomical terms. It's about 10 to 20 kilometers per second, and they're wider. So they go out like a flower in a way, you could say, or
Hmm.
an onion in a way. Jets are more just straight out, and winds
Right.
are
How
so.
how
Yeah.
thin or thick, shall we say, is the jet as
So
it's coming out?
yeah, so the width of the jet can be like in that paper. It can vary with like which star and then which jet. So one of them, the narrowest one, I think, was less than 20 AU wide in width itself. We
Hmm.
could not even resolve the width of it because it was that narrow. And JWST pixel is still about 14 AU for that distance for these
It's
stars, these
ridiculous.
nearby stars. It's still 14 AU, and then we so you cannot actually see planets with JWST, but because these floors are like thousands of AU, that gives us enough number of pixels to do a lot of with it. But then we've also seen jets which are 50 AU, 100 AU wide. It's
That's ridiculous. It's just hard to imagine. Like this, it's weird to say that it's a focused jet when you're saying it's 40 times the width of the distance from the Earth to the Sun, and that's a focused. And just trying to
That
imagine
is, yeah.
a singular jet of matter that huge in one direction. It's that's almost like something out of sci-fi. That's crazy. That's a huge amount of space.
It's kind of like a Death Star beam, right? But bigger.
Like a solar system beam. Thanks for the sound effect.
Actually, the craziest thing that I'm like very excited about right now is, I mean, last year we published this paper. There was 4 stars. The year before that, when we did a press release, there was 1 star. We're looking for something else, similar something else. But now I have a NASA funding to lead a project where I look at not one, not four, not 10, 74
Oh
stars
wow.
and JWST observations of all of them. And these are
Whoa.
all data that is available right now in the archive for anyone. Um, and it's amazing. I mean, the number of jets we are seeing, the number of winds. For the first time, we are actually resolving them, have images of them. It's just amazing.
And are you seeing that also like 50-50 split in terms of symmetric or asymmetric jets in that sample?
So in this sample, it will be a little harder to say because in the other sample, the 4 disks were all edge on, right?
Hmm.
So if I'm looking above and I'm looking below, I'm not biased or anything. I know the asymmetry, I know the symmetry. In this sample, these are not all edge on. These are not all completely side view. I have 60 degree, 50 degree, 70 degree. In that case, what happens is the flow that is going away from me, there is a disk between me and the flow, right? So I don't know how much it's blocking my view of the other side. So it's always going to look smaller. But then is it really small?
Hmm.
So that is a question that we don't know. Uh,
Interesting.
but there is definitely asymmetry. There's all sorts of asymmetry, not just in the jets, also in the winds.
Is this doing well? This is common across all protoplanetary disks that you're saying. Does that mean our solar system at one time had these ridiculous
Hundred
jets
percent,
shooting out of it?
100%. My answer would be 100%
Planets
for
that
that.
could have been.
Before,
Immediate yes.
yeah, before Earth formed, before probably a lot of these planets formed. I mean, also think of it another way, right? So when these planets are forming, we know from looking at thousands of disks that the amount of gas you have in the disk is 100 times more than the dust in the mass, not in size, in mass, right? So that's a lot of gas. Where is all that gas today? When you look around, you see rocky planets, you see Jupiter-like planets which still have a core. Of course, there is a lot of gas in these planets, but if you account for all of that, it will account for about, I think, 10-15% or something. Where's the rest of it? So the rest of it actually left the system
Through a jet, I guess. Is that
through jets and winds, and there are different types of winds. So there is one MHD winds, which is more because of magnetic fields, but we also think that there is a thermal wind, which is more sort similar to like evaporation, just because of the energy just evaporates into space.
MHD for listeners who aren't familiar is magnetohydrodynamic?
Hydrogen.
Is that
Yeah, yeah, yeah. So essentially, it has to do with magnetic fields. The other one does not. So there's two distinction. So I'm trying to see whether these two types of winds act at different times in evolution, or they are all coupled and everything. So that's something we'll test and see.
cool?
And these jets we see that you're studying, these are off of protoplanetary disks with just one star. Does it happen with 2 star systems, or is that just too far down the road?
That's a super interesting question. So it does happen with when there are 2 stars at the center, but I think then the question becomes how far apart the 2 stars are. I think if they are very close to each other, it's still possible to have something like this. When they are a little farther, then I think it becomes difficult, and then they're very far away, then they have their own protoplanetary disk. So that is again very much possible. So one of the things we did in this study was this wiggling, which was which was, to be honest, the most exciting part of the paper for me, because I was working on this when my advisor was gone for conferences and trips and something for like 2 months, and we'd done much of the analysis. We'd done all the other stuff, and I was more looking at the data. I'm like, okay, what more can I extract out of this? What more can I do on this? Um, and then I started studying that these jets, when they go out, they don't shoot out straight. They sort of wiggle as they go.
Hmm.
The question was essentially, why are they wiggling? And one of the ways is, if you have two stars, right, and think of one of them is ejecting the jet, and here the jet is actually ejecting near the star, not the disk, right? So if it's moving, then the flow is going outwards, and it's moving in a circular direction. So it's going to look like a, you know, spiral in a way, if you think of the whole motion. What is interesting is it going to look very similar on both the sides of the disk.
Hmm. Symmetric wiggles.
It will be symmetric. However, if you have a disk from which these are launched, and the disk, let's say, bends towards the left, so one side goes left, the other side goes right. So this is asymmetric. So it's very common to find asymmetric wiggles. Find them relatively often, and we have an idea that okay, it's because of the disk is itself, moving. But then in one of these objects, I actually found symmetric wiggles. That is, they are exactly like each other on both the sides.
I
And
have a
just
dumb
based,
question.
yeah, yeah,
Oh,
please.
sorry, go on.
So just based on this, you can sort of figure out, what is the mass of the two stars, what is the period, how like how close they are, how far they are, how quickly they're orbiting, and so on.
Okay, so this is exactly my questions. I was having a quick look over your paper, and I found it really interesting that the mass of the second star that you found looks more like a brown dwarf sort of mass, which is super interesting to see brown dwarfs forming in that way.
Hmm.
But the period was on the order of like a year or two, right?
Yeah.
So so how correlated is the period of the wiggle to the period of the orbit? Because I'm imagining, like, James WST, the data is so hard to get even just a few hours. It's not like you were staring at it for 2 years to see the wiggles. How does that work?
So the beautiful thing with jets is you don't have to observe it 10 times to see how it changes with time. You
Mhm.
can see it once and you can see how it changes, because when you see 1000 AU of jet material, this 1000 AU of material was ejected at different times, right?
Mm,
So the farthest away material was ejected the earliest. And when you check with kilometers, 100 kilometers per second, and so on, so you figure out that this material was about 20-50 years ago. So you're seeing all the history in
it's
just
a
one
time
snap.
machine.
So when you see these periods and everything, it's telling you the period of the binary, because as it ejected over time, it gave the wiggle to the jet.
That's so cool.
Yeah, I guess that makes sense. It can't change course once it's left.
Exactly. The important thing is the periods cannot should not change of the jet that you're seeing. Otherwise, there's something weird happening.
That's crazy. Is there a way to kind of, since it goes out so far, can you like trace how far back can you see like a trail of the ejected gas that's left the protoplanetary system?
I
I
mean,
mean, I'm assuming it's just as it's spinning and it's wiggling out material. I mean, it's going to disperse and disperse and disperse over time, but does it leave like a little contrail, I guess you could say, like a plane through the sky?
no. I mean, if you look for like images of jets online, some of the most beautiful images that you'll see, like those have been part of like press releases and stuff. Um, they're like parsec scale long, so thousands and thousands and thousands of AU. I mean, you can, it really depends on which star, what is the age, and all of that, and then you can see really long jets. But then we've also seen jets which are like only 20 AU. So there's all, again, all shapes and sizes, and there's so much variety. Yeah, you can see like even 10,000 AU sometimes.
This is crazy. I told you from the start, Benjamin. I knew that this was going to be a super interesting one.
In our chat leading up to getting on the call, the word amaze balls was used more than once. And we didn't even talk to you yet.
I think I said it was going to be so amaze balls that it was an amaze ball pit.
Yeah, that's exactly what it is.
Mm, yeah. Actually, another crazy thing about jets, if we are on this,
Please,
it
yeah.
it can
Bring
make
it.
more
I'm
stars.
here for you. Go
So
on.
It makes more stars.
because you have this 1,000 AU, 10,000 AU jet, right? And it is happening in the region which is forming stars, because it is itself ejecting nearest forming star. So you have other clumps. All they need is some energy to collapse and make a star and a disk. Jets can give you that energy because they're launching from this star, but if your other star is on the way,
That's
they will
enough to trigger
collapse
it.
it. They'll trigger it. So they can form more stars.
Oh yeah, because these are so these sort of baby stars, right? They're like young stellar objects or T
Mhm.
Tauri stars. They're more common in nebulae, right? Like stellar nursery sort of nebulae. So the surrounding environment when you go a couple of parsec away are just going to be these clumps of gas ready to. Oh, this is so cool.
Yeah, you don't even have to go parsecs away. Sometimes it's very close by that there
Mhm.
was, some dense material that just wasn't able to form a star, and then this just triggers it. It's crazy.
How long
I love
does this period of time in a protoplanetary disk last? This ejecting a jet. I mean, when does it start? When? What? At what time? At what point do you say that the jet has now begun? When the star turns on, or just the magnetism of the cloud coalescing itself? And then, does it ever stop? Like, is our solar system still trickling stuff away in a very fine, 2 atom thick jet?
So it's very interesting. So the earliest we can say is pretty much whenever we look at a protostar that is in the shape and form of a protostar. So anything that is not that has collapsed is ejecting material in one way or the other. So it starts basically as soon as the young star is starting to form, in a way. When does it end? The jets actually, I think they end. We don't have a concrete answer to this, but I think they end about 2 to 4 million years of age of the system. But again, it depends on a lot of things and a lot of factors. But definitely by 10 million years, by 10 million years, because we know by 10 million years most of the gas in the disk is gone, because that we can trace, right? Because when you have
it.
1,000 stars, you statistically can see them at different stages of evolution and different ages. So you can see a trend that at the earliest ones, the 0.5 million year old ones, have
Mhm.
those all have this gas disks. But then by 10 million years, you've gotten rid of all the gas. So by then, it's definitely gone. And with the sun, so it's not exactly ejecting a jet, but there is something called a stellar wind, um, which it still does. I mean, that's the energy sort of we get from the star, the sun itself. So there's some form of it that's still there,
Hmm. So
and
still
it is also
ongoing, just
very,
at a lower
yeah, it
rate.
is also very high speed. It's like 200, 300 kilometers per second.
So cool.
It's ridiculous.
How did you, if I can ask, how did you find yourself focusing on protostars and protoplanetary disks?
I mean, it mostly happened by chance. I mean, that wasn't really my choice, or I never really had a choice. So it kind of started by chance, but now I'm stuck into it. By chance, by what I mean by chance is I was looking for a research project during my undergrad, um, and I was shooting emails here and there, sending messages here. I'm like, anyone who gives me anything that is to do with astronomy, I'm happy. And after about 200, 300 emails, one of this actually stuck. And then that person, Goran Sandal, he worked on very young stars, even younger than what I'm studying right now. at the youngest stage, 0.5 million year kind of stage.
Hmm.
And then there I studied outflows, or these are called outflowing gases for the first time, and then that sort of creates an experience for you, and on the basis of the experience you get a PhD to do something similar but not exactly the same, and then that sort of uh, I got trapped into this in a way, you can say, but I enjoy it.
I mean, you definitely seem to enjoy it. Like the way that you talk about the stuff, you've got a smile on your face. You're excited to share. It's yeah, it worked out well, even if it was somewhat accidental.
Oh, definitely. I would say so.
It's such a common theme. All the best science is stumbled into. Just, I wonder what happens if I look at it this way.
And it's like a former guest, multi-time guest, Sarah Amidor was saying, right? So she's a
Mhm.
multidisciplinary biologist, and she was saying how she views herself and a lot of scientists as kind of like somewhat hyperactive Labradors. It's just like, oh, what about this? Oh, this is cool. What about this? Oh, this is cool. And that just becomes your career, right?
That is so true. Yeah, I mean, I'm focusing on this right now, but going forward, I have no idea, what I'm gonna do. I may, because I mean, jets are so universal. I may even shift to black holes and be like, okay, let's study these jets. Why not?
Yeah, those are some next level jets, all right.
Yeah, I may have evidence for actually a brown dwarf also ejecting a jet, which will be like the lowest mass
That's up
object
Covy's alley right there.
that's ejecting a jet, which is,
Yeah,
but
we should we
sure.
should we should talk afterwards about maybe collaborating on that because I've brown dwarfs are near and dear to my heart.
Yeah, that might be crazy. Like if brown dwarfs also have a jet, I think that would be more in the zone of, okay, brown dwarfs to form like stars and not planets. But that's too far from home for me to claim, so I'll keep it here.
But you never know.
Yeah. And one of the cool things about science is that it's collaborative, right? So even if it's a little bit far from home for you, you find someone else who has
Oh,
a bit
definitely.
more
Yeah.
experience, and it's nice. I've always liked that we can kind of like complement one another's skills and gaps in knowledge. Nice. One other background question I wanted to ask. I don't know if Benjamin had this on his list of questions as well because he thinks that I'm reading his mind today. But your background originally wasn't astronomy focused, right? You were originally more on the engineering side. Um, so before you sent out these hundreds of emails to astronomy professors, was there one individual moment that made you say, "Yeah, maybe not engineering. Maybe I'll shift my path this way"?
I think there were two things. One was I got inclined towards astronomy during my high school, and and that was mostly YouTube documentaries, CBS, PBS Space Time, and Michio
Nice.
Kaku, and Neil deGrasse Tyson, and all of them. Just hour-long documentaries every day. So that was fun. But then I had to sort of talk to my professors about career path on what should I do. I knew that what I'm seeing on YouTube is not the life of a scientist on a daily basis. So I may not like that. So I had to choose wisely in a way. Um, and the situation in India is that if you do a bachelor's in physics or pure sciences, generally, you kind of have to do a master's and a PhD after that. Otherwise, you don't have a job. You don't
Mm,
have good prospects for a job because you have 1.5 million engineers graduating every year in India.
Wow.
1.5 million engineers, and we don't even have jobs for all 1.5 million of them, right? It's less than a million that we have jobs for. So, that was a decision point, and then it means that if you do engineering, you don't have to be stuck with engineering because not everyone's going to have a job at the end of the day anyway. So we have, Bollywood actors who are engineers. We have management people in different companies, CEOs, chartered accountants who are engineers, and all sorts of things engineers can do. So I was told that, I mean, the discussion was basically that, okay, I think we should choose engineering because I was getting a good college. So that would be a safer option. And I can always switch to astronomy if my interest still remains in that. And I think it was like the engineering is 4 years. After 2.5 years, I was always part of this astronomy club of my college. But after 2.5 years, there was this one workshop in Pune in one of the astronomy institutes, which was 2 week long, and I just fell in love with it, completely all over again. And then that was the deciding point where I was like, okay, I am doing engineering. I am doing astronomy. I'm not, doing engineering. And then 2 or 3 months after that, we had the COVID shutdown, lockdown, which for me meant that I can stay at home, minimize my engineering lecture screens, and work on astronomy, which is what I did for like a year and a half, and then uh, entered astronomy. So, but yeah, to get into astronomy was pretty difficult because then again, the question is, we have, these many physics students. Why would I hire an engineer to do physics? So that became a difficult job. So that's why I had to send those 200, 300 emails around and so on. And then this one guy, Goran, he was, I think at the time, 72, 73 years old, retired in Hawaii. And he was like, okay, I have a few projects in the back burner that we can, bring up. And he had time because he was retired. So he could actually guide me and like teach me, which was very helpful for me. And he like single-handedly brought me into astronomy, one can say.
Wow.
Big
Yeah,
shout
shout
out
out to Goran Sandel. Good on him.
mind reader.
Sorry, I won't steal any more of your questions, Benjamin. If you have more questions, I won't ask them.
Ah, golly. Silly question. With all your looking at JWST photos and such, and you gathering all the information, just tell us the truth. Have you ever printed one up so big you make it a wall art of it and it's hanging in your house right now? Because I would. I was just thinking, if I took a photo
I'm
at
I'm
JWST,
still I'm
I'd
kind of still
frame
looking
it.
for like waiting for a great image that I publish. I think with- there are amazing pictures of winds and jets from stars with JWST. Those are not mine. so so if I stumble on something, that's crazy. Maybe I may do like, because now I have not a crazy image, but many images from many different stars. So maybe I can do that actually.
Like a
I can.
collage of all of
It's a
them together.
collage, yeah, yeah. Because I'm gonna publish it anyway, so I can just crop the collage, the interesting ones, and then print them. That's a good idea. Thanks.
As long as you send us one.
Yeah. Yeah, yeah, yeah,
Yeah.
yeah. I'll give you my address and
But
everything.
I'll send you the link to the paper.
Okay.
Yes, please do. So cool. So we have a special segment on the show called Questions and Quibbles. It's a rapid fire round. Are you both ready for it?
I'm ready.
Can never
Go.
be
Get us off,
any
Cody.
less ready, I guess.
Okay, so maybe as a way to lead into it, I did see this really cool short story that you wrote for the International Astronomical Union's competition for short stories, where you basically threw out all of the old constellation art because none of them make sense and you can't always see them. So you just said, I'm going to make my own. I'm going to turn Orion into a rocket and the line of stars around it, that's like the no-go zone around the rocket. And then the Pleiades turn into this group of astronomers who are watching the rocket launch. I thought that was super, super cool. Just putting that out there. But in terms of looking up at the sky and everyone, especially as kids, seeing different things, what was the first question? Is what is the weirdest thing that you believed as a kid?
Benjamin, you wanna go first?
No, this is just for you.
This is for you, yeah. Benjamin's helping me ask the questions.
I'm up and ask.
Um, Well, I guess so. There's a saying in India that whoever's dead is in the stars. So like one
Mm,
star is one person who was dead. So like your grandfathers or forefathers essentially. So I did believe that for like a year or two, but of course didn't believe it long enough to enter astronomy to answer that question. What they really are.
that's cool. I didn't know
Yeah.
that.
That's a nice one. Next question. Which teacher had the biggest positive impact on you?
I'll have to say Gordon.
Yeah,
I think, yeah,
He
because I
set you
mean,
down this
just
path.
yeah, exactly.
it's so nice. All right, next question. What is one scientific discovery that you wish you could have witnessed in person?
Beetlejuice exploding. If I
Oh, a
could,
future one.
yeah, yeah. If Beetlejuice explodes in the next 50 years, that would be a spectacle. We'll have another moon in the sky essentially for 7 days. Cannot wait for that.
Hurry
A
up,
supernova
Beetlejuice.
going right in front of us. That's crazy. Also, scientifically, how much we can learn about supernovas is
I love it. It's an awesome answer. I think it's the first time, correct me if I'm wrong, Benjamin, that someone has suggested a future event that they would
First
like to
one.
witness rather than a past one. Nice.
First one. If you had to pick one historical scientist to go bowling with, who would it be?
I'll say Newton. I don't know why. Um Cambridge is cool. I was in Cambridge 2 years ago. It's a great place, and I wonder how in 1600s they did bowling.
Bunch
That'll
of
be
wooden
fun.
balls. That's what it is.
Nice. All right, next question. This is a serious question. If you were a sandwich, what kind of sandwich would you be?
Well, I'll have to be one of Indian McDonald's sandwich because let me say, Indian McDonald's hits different.
Really?
Wow.
They have options in vegetarian sandwiches and like burgers and everything, and you have a potato patty is with spices and everything. It's amazing.
I've heard that McDonald's around the world offer different things you cannot get here in the States. Like
Exactly.
that sounds amazing.
Yeah. In every country because they have to cater to the local taste. So
Yeah.
you have Mac Maharaja burger, which is essentially a huge burger. Maharaja is like king. So Mac King, so it has like double patty and then layers and layers. And it's crazy.
You know what? Forget the beautiful scenery and the culture. I'm going for the McDonald's. Probably wouldn't even have to leave the airport. Just land and eat it.
Yep.
What is your most controversial opinion about pizza?
Well, I know where this is headed. My advisor is Italian. I do not think that pineapple on pizza is bad, to be honest. So
Yes.
that's probably
Right answer.
controversial to my advisor at least, who
I
hates the
love how
idea of
people think
pineapple on
that
pizza.
we're asking this question to kind of beat around the bush and say, "What do you think about the pineapple thing?" It's not. We just want to know what you think.
But historically, I feel like that this is basically the question that we've accidentally been asking because
Yeah,
most people will give a strong opinion on pineapple on pizza every time we ask that question.
I think the best
That was
answer
so
we got on
random.
that was someone said they like to eat the pizza crust first and then work their way towards the corner tip of the slice. I'm like,
That's
that's
controversial. Yeah,
controversial.
yeah, yeah.
The pineapple's just your taste preference.
Well, at least in the US, there's no way you can eat the rest of the the crust when it's dry and cold. It's impossible.
Crazy.
All right. What is, slightly back on the science, what is your favorite scientific word or phrase?
Um, I think my favorite one is it's right there in my brain. Um, Consistent.
Consistent.
because um, and we were just having this discussion today as well, like a person was presenting the result and I was like, so do you think that your observations are consistent with this particular theory, or are there strong evidence for this particular theory? And they said consistent, because consistent is a very easy way out, you know. And scientists, they like to be very safe, or like they like to play it very safe by very particular words, and I think consistent is one of them that they use very often to be safe.
It's a really cool answer. I like that.
Okay. Next one is, what is your least favorite scientific?
My
Inconsistent.
Inconsistent.
inconsistent. Well, it's my least favorite when it happens to my research. um, Maybe conclusion, because a lot of people like say conclusion, but they don't really have one.
That's funny.
I guess, yeah. I guess to tie those two answers together, it's something that I think is important for scientists to learn. And normally in grad school, you pick this up. The idea of like proving something, especially in astronomy, it's not necessarily ever going to happen, right? You're talking about stars that are billions of kilometers away, right? And we can find observations that are consistent with the theory. They can provide strong evidence for a theory, but our conclusions will never be proven, right? In the same way that you can have certain levels of certainty. It's a tricky one.
Yeah, and also like just because of there's so much variety to it, like every star comes with so many different things that you can maybe pin down the fundamental physics, but then something else is going to change that will change how it looks, and then you'll have exceptions and outliers, which
Yeah.
always makes it more tricky.
All right. Next question. What is your favorite useless science fact?
That's a it's actually a very tough one, to be honest. Um, I I don't know. I'm blank completely.
Maybe I could phrase it differently. Is there a protostellar, protoplanetary disk system with winds and a jet that most resembles the Big Maharaja burger?
There is one. It's called the hamburger. The disk is called the hamburger.
There
Actually,
you
Really?
go.
very useless.
See?
Actually, yeah, there's hamburger. There's also the butterfly disc.
The butterfly disc, the hamburger disc.
Yeah.
Lovely names. Very fun, not useful.
But thanks for the lead,
Okay.
though. Yes.
If you could rename one planet in our solar system, what would you call it?
Well, it has to be Uranus, right? I mean, because every time there's a professor who's giving a lecture, there's a quiet giggle in the back. So I'll probably rename that to. Um, hmm. Well, I'll probably rename that to hamburger, you know, because why not?
Why not?
We have Jupiter, Saturn here. Jupiter, Saturn, hamburger, Neptune. That's
I'll take it. I'll take it.
For your next postdoc, you'll just be like going around to every solar system map in every classroom across the US, just putting a little sticker over Uranus and saying hamburger.
Hamburger.
All right. The last question, this is a big one. If you had to sing one karaoke song to save humanity from an alien invasion, what would it be?
Well, it will definitely be a metal song.
Sure, sure.
Let's go for In the End, Linkin Park.
Oh, love it. That way, even if your singing doesn't save the planet, at least the song
It
choice was
doesn't matter.
appropriate.
Yeah.
Nothing. Yeah.
I'll take it.
This is great. Naman, thank you so much for joining us.
Yes,
This was a
thank
lot
you
of
so
fun.
much.
Of course,
Super.
thanks for having me. This was amazing. Yeah.
If people want to learn more about, if they want to connect with you or if they want to learn more about your research, is there somewhere online we can direct people to?
Yeah, I mean, emailing me is always a great option, but also I'm very active on LinkedIn. So LinkedIn could be one of the ways. I also have my own website, so you can check that out, namanbajaj.github.io. So from there, you can also just straight away send me a message, and that will come to my email, and I'll reply and everything. So that's probably the easiest.
Fantastic.
Awesome.
How about you,
And Benjamin,
Kovi?
do you
Where are
want to?
you?
Me?
You
Where am
first.
I? I'm
Yeah,
in
where are you?
Sydney. Where?
Oh, okay, good.
On the internet. On the internet. You folks can find me at Fun Fact Science on all the social media platforms. What about you, Benjamin?
You can find me under Science, actually, on all the same platforms you'd find Kavi. Um, Facebook's the big one, but Instagram and LinkedIn and wherever else. And of course, you can listen to this anywhere you listen to your podcast, and you can watch us on TikTok and on YouTube. That's right, Naman, you're going to
Yep.
be on YouTube soon. And yeah. So you can look up the Nerd and Scientists on where you look up your podcasts, and also on YouTube, TikTok to find and watch the show.
Old episodes, new episodes. If you have any requests for new guests or new topics that you want us to discuss or to chat with, let us know, and we'll see you next time on the next episode of Science Actually Presents The Nerd and the Scientist.